Good afternoon, good evening, good morning, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a senior astronomer at the SETI Institute, and today we are going to talk about the next big challenge in astronomy, how we are going to image exoplanet with life using a space telescope. And for this, I invited someone who gave a very interesting talk at the SPIE conference in July in Montreal, and I have the opportunity to see her talk about this technology. Rhonda Morgan. Hello, Rhonda. How are you?
Hi, Franck. I'm well. How are you?
Good. Where are you calling us from?
I'm calling you from the Jet Propulsion Lab in Pasadena, California.
Okay, so Rhonda, you an associate technologist for astronomy and physics at JPL and Caltech. You're the lead of the Exoplanet Program Office Standard Science Evaluation Team. You have worked on a lot of space mission concepts in the past, and today we are going to talk about specifically one of them that with a code name called EROOF, but we are going to go through that first. So before we go through the telescope and the technology, I would like you to explain to us and our viewers what is the Decadal Survey and what we should care about that.
Yeah, that's a great place to start. In fact, I have a slide that shows the past decadal surveys. So every 10 years, the National Academy of Sciences does a survey in astrophysics, and they collect white papers from the community. They get hundreds of white papers, and they put together large committees of experts in astrophysics that read the papers, and they arrive at a consensus of what's happening in the community. And they want to know what are the questions that are being asked, and what's a good way to answer them. So I have a copy of this decadal survey. You can see it's pretty extensive, and there's a history that I'm showing in this slide of the decadal survey recommending the flagship telescope. So, for example, the James Webb Space Telescope was recommended in the 2001 decadal survey, and it took until now to get it launched and commissioned. You can also see that the Hubble Space Telescope was recommended in the 1972 decadal survey, and that launched in the early 90s. So we're very excited that the recommendation for this 2021 decadal survey for the next flagship is a space telescope about 6 meters in size that would be capable of directly imaging an exoplanet, so that's a planet around a star that's not our star, of the size of the Earth that could be in the habitable zone. So that gives us the science goal, and it is really a technological challenge, as is an exciting thing to be working on.
Thank you. So let's go later on this. But before that, I want to say that mention that we have viewers watching us from Mahwah, New Jersey, from the UK, from the Philippines, from Italy, from a sofa somewhere on Earth. I love when there is a name like that. Nokoji Wanong. So I don't know where this is, but hello, Providence, Oklahoma, Louisiana, and someone from the Azores again. Hello, back, you're back. I just recognize your name. And Mexico City. So we are talking about the next generation telescope that could image an Earth-like exoplanet. So the Decadal Survey made those recommendations. He arrived late in 2022 this year because of something happened in the world. Um, and so now in the Decadal Survey, we have this recommendation, but we have very specific requirements, right? What are those requirements? What the Decadal Survey say about this space telescope?
That's right. When the Decadal Survey recommended this size of space telescope, it was based on some studies that had already been done about what if we had a 4-meter telescope and how many Earth-like exoplanets could it see, and what if we had an 8-meter space telescope, and they said, well, it's not just the size, it's also how long it might take to develop that, and also what kind of funding they thought might be available. And so they created this a proposed idea of a 6-meter space telescope that would be able to survey the nearest 100 stars' habitable zones. And we think that maybe about 25% of those stars could have an Earth-sized planet around them in the habitable zone. And so that's the science goal for the mission. Now, Not all of those Earth-sized planets may have biomarkers on them, but we want the mission to be capable of looking at that.
Okay, so let's call this space telescope ERUV. That's the code name that's being used around with others, but let's call it like that. So we have a space telescope. We want to design a space telescope that will be able to image 100 exoplanets and specifically detect biosignatures. So maybe you could explain to the viewers what is a biosignature.
Sure. Let me also say that ERUV stands for the IR optical UV, because that's the wavelength range that this telescope will have. And it will be used not just to look for exoplanets, but also to do some really groundbreaking astrophysics work. So I do have a slide that shows what the Earth looks like. This is the famous, let me go to the next slide here. So on the left is the picture of the pale blue dot, which Voyager took from the distance of about Neptune. And the Earth is just 1 pixel large in this. And so if we try and image an Earth-sized planet around another star, it will also be only 1 pixel. It will be very small. But if we break apart the light into its rainbow and we look at the fingerprint in the rainbow, we can see different important molecules. What we would like to see is if there's carbon dioxide, which could point to there's an atmosphere or there's not an atmosphere, right? Because Mars has a lot of carbon dioxide. It has an atmosphere. But it doesn't, and then we want to see if there's water, because if there's water, then there's the possibility, especially if there's liquid water, then there's the possibility that life could form there, we hypothesize. And so then we might want to see other things like methane, so, an organic molecule. And we would really love to see if there's oxygen, because oxygen is produced through photosynthesis or through non-equilibrium geochemical processes. So those are the things that we would be looking for in the rainbow of light from the planet.
And this is if we want to look for life, which looks like the life we have on our own planet. That's the kind of idea. So it's really to find an Earth-like exoplanet. We're not talking about geologically speaking only. We're talking about an ecosystem that will be very identical to our own planet biosphere. We have people joining us from Mexico, from Riverside, California, from Huntsville, Alabama, from Wisconsin, from the Netherlands, from Guatemala, from Vancouver. Welcome. We are talking about the ERUV project, a space telescope that could image an Earth-like exoplanet. So, Rhonda, to image an exoplanet, it's not something easy, right? I mean, I've been working in this field for a sufficient amount of time to know how difficult it is to find a planet, to image a planet even. Can you tell us a bit about the technology that could be used for that?
I would love to. So imaging an exoplanet starts with suppressing the starlight. So the star is just bright, and it's so bright that you can't see the exoplanet. It's like when you're driving into the sun and you can't see the road, right? What you do is you put down the visor so that you block the sun. And that is the same concept that we use. We have to block the star's light. We have to create an artificial eclipse so that then we can see the exoplanet coming through it. Now, doing this for an Earth-like planet is really hard because the contrast is, for people that are safe with exponents, 10 to the 10 times brightness ratio between them. So that is 1,000 times harder than trying to see a firefly next to a searchlight in New York City from here in Los Angeles. Mm-hmm. Right, that's very hard. Now, we have 2 main approaches for doing this. One is to provide this eclipse outside of the telescope. And so this could be like a really big, we call it a star shade, and it has a very special shape to control the light and create a really perfect shadow. And then the telescope sits in the shadow. And then we can see the planet just off to the side. I do have a slide that illustrates that. If we could bring that up. Thank you. I will go to here. So here on the left is we see the shape of the star shade. And then we've got this little illustrated haze of starlight coming around the edge, but then off to the side, we can see these couple of hypothetical planets. Now, the other way that we can cause the eclipse is inside the telescope, where the light comes to a focus, as we see in this graph on the right, where the light comes to a focus, you put in like a little glass slide with a very specially shaped dot on the slide, and that will block out the star's light. Now, in order to do this, the shape of the light has to be really perfect and exact. So exact that you need a way to change the shape of the light even when you're in space. And so this mirror at an angle is called a deformable mirror. So it's like a thin mirror that has all these little actuators on the back that help it change shape to control the light reflecting off of it perfectly, so that then you can see the planet. And
so that's for adaptive optics for the people who have been following our SETI lives in the past, right?
That's right. That's adaptive optics. And technologically, these are both really hard, because when you have a contrast of 10 to the 10, that means that somewhere in your system, you have to have a precision of 10 to the 10. So here with the coronograph and the adaptive optics, you have to control and stabilize the quality of the light to 10 picometers over tens of minutes. So keep in mind that the radius of a hydrogen atom is about 100 picometers. So you need everything stable to within 1/10 of an atom. Now over here for the star shade, that's big. It's about the size of half a football field. And those little tips have to be placed really precisely to about 1/2 millimeter, right? Oh, so maybe like the thickness of the white of your thumbnail over a football field.
Mm-hmm.
Now, both of these are challenging, but we do have hardware where we've been trying to get there, and we're closer than we've ever been before. We are, in fact, excited that the coronograph, we're actually going to fly a coronograph in space, and this is on the next flagship mission, the Roman Space Telescope, and it has a coronograph instrument. Now, the contrast that it achieves is not going to be as good as what we need for EARUV to look at Earth's, but it should be able to see some Jupiter brightness planets.
Yeah, this adaptive optics system in space is being tested already on the ground for years. And now we are going to have one in space, which is exciting. I mean, when is the launch of the Roman telescopes? 5 years?
I think it's no earlier than 2026.
Okay.
It might be as late as 2027. I'm not the right person to get a precise answer on that.
It's tomorrow, basically. For us, it's tomorrow. The next 4 or 5 years is basically tomorrow for an astronomer. So we are going to have an adaptive optics system in space to test this technology. Mm-hmm. And what about the star shed? Do we have plans to have a star shed in space in the future?
We don't currently have plans to put one in space. We've done a lot of work on this on the ground, working on scale models, little tiny disks, because diffraction works at all the scales. And so we did achieve a 10 to the 10 contrast with a little teeny tiny star shade. And then the mechanical precisions, we do that like one of those petals at a time. Or we also look at the inner disk that has to deploy. Then we look at scale models of that. So there's been really fantastic technology development work done over the last 5 or more years by a project called S5, which stands for Starshade to TRL5. And we have made a lot of progress in that.
Okay, so we have kind of a mandate from the Decadal Survey, a scientific goal. We have 2 existing technologies so far. And the reason I invited you is because I really like your talk, where you basically went through different technology, different type of filter. Can you tell us the work you did and you presented at the SPIE? Maybe a bit too complex, but I like the rough idea.
Yeah, thank you. The main thing that I was trying to model was how many exoplanets would we be able to see? So the first question is, can we just find the dot? And then the next question is, let's image it several times so that we can try and figure out what the orbit is. to know if it's in the habitable zone. And then the last step is let's take a picture of the rainbow. And one of the things I was showing in my paper was, well, what is the quality of the fingerprints that you want to get in the rainbow? So you can look at different colors, and that impacts how many you can see. But also, like, if you want to get a lot of those colors or just a small number of those colors, then that also impacts how many you can get.
Mm-hmm.
Um, so, and I also looked at, well, what happens if you know a little bit ahead of time? This is an exciting idea for us, because maybe if we were able to build an extreme precision radial velocity instrument, so this is something that's on the ground and it watches the wobble of the star by looking at the Doppler effect of the star. Now, the current systems aren't sensitive enough to find an Earth, but maybe with a next gen one, if we could get them to be sensitive enough and we knew where some of those Earths are, we call that prior knowledge, knowledge that we know ahead of the mission. And so we can start looking at the rainbows from those planets right away. And that saves us mission time. Because maybe if we find something really interesting, we would want to look at it a lot. So that's one of the other cases that I looked at.
Yeah, because for the viewers, we are going to build this probably in 10 years, and it will be on the sky in space in 20, 25 years. So in the meantime, a lot of technological development will be done here on Earth, and we probably have a better understanding of the type of population of exoplanets in our surrounding using other technology like radial velocity you mentioned, but also transiting exoplanet and maybe some other that we did not even envision yet that they will exist in 10 years. Maybe there is someone will come out with a new idea. Astrometry with Gaia, which is extreme precision, something like that. So we will know that there is, if there is a planet around some of the stars in 20, 25 years. So with this telescope, we will not only know, we will know the planet itself, what the color is of the planet is, and we will also be able to study this planet. So what kind of study will we be able to do? Can you kind of extrapolate a bit about not only the color, but what will be the final result?
Right. So, we don't know how much we're going to know in 20 years. And some of that depends on investments that we make now, right, to try and find those things out. So for now, we're thinking about this concept as, well, what if we don't know anything and it has to find out everything? So it has to discover the little dots and then look at the rainbows. So one of the first things that we look for in the rainbows is there water? So we look at a particular wavelength range. For people that are interested, it's 800 to 1,000 nanometers. And that's an interesting range because if it's a planet like the Earth, water is really deep and broad and easy to detect right there. Now, if it's not a planet like the Earth, like if it's a planet like a big gas giant planet that had methane, that would be easy to detect right there. So that's one of the first things that we would look at so that we could help categorize which kind of planet might we be looking at, right? The next thing that we might look at is the 20% bluer region from around 700 nanometers to 820 nanometers. Oxygen has a really deep line there. Now it's narrow, so that means that we have to have an even higher quality rainbow to look at. So we have to integrate a little bit longer to get there. And so we would be looking for a deep oxygen line right there. And then if we go a little bit broader, and we say we go down from 500 nanometers to 700 nanometers, now there aren't any molecular lines that we might be able to see. But if there is an atmosphere, it'll have Rayleigh scattering, which is why the sky is blue. So we would just look for, does it get brighter as it gets bluer?
Very good summary. Thank you, Rhonda. So there is something, someone posted this comment here, is that it's very humbling to think that we will see maybe in the future in one pixel an exoplanet, right? And in this pixel, by analyzing the color and spreading it in different wavelengths, as you mentioned, we will get information about this planet. But the reverse is also true. And that's not something I prepare Rhonda to say, but I'm going to say it. if there is a civilization somewhere in our galaxy which is 25 years more advanced than us, maybe they have this E-roof telescope, and maybe they can see us right now in one pixel and see the signal of our own planet and the presence of life in on our planet. Only 25 years. That's nothing.
Wouldn't that be exciting?
That would be exciting. So, I mean, we have been developing adaptive optics for the past, the first system was in 1991, if I remember. I worked on the first system in Chile in 1996. So that was very new technology. And now we are making a lot of progress, and now we're thinking about adaptive optics in space. What do you think will be the next big technical advancement in this field? Can you extrapolate?
Well, let's first take a moment, since we're appreciating history, and appreciate that the history of exoplanets, right? That the first exoplanet was really found in 1995, right? And the first directly imaged brown dwarf happened in 1995. So exoplanets as a field is still really new, right? And in that, and since 1995, we've actually discovered and confirmed 5,000 exoplanets. I actually have a slide on this, if we could bring it up. So what kind of exoplanets have we found? As you can see from here, we have found a lot of gas giants. We found a lot of Neptune-like planets. So these are like colder gas giants. So they're similar, or they can also be a little bit warm. We found super Earths. So we found things bigger than the Earth. But only 4% of the planets that we found are what we call terrestrial, which are small and rocky. And so they're closer in size to the Earth. Now, does this mean that there's only 4% of them out there are terrestrial? No. This is completely biased by the sensitivity of our techniques to measure these, right? So when we, if and when we get to build IRUV, we will know this much better, right? It's just that right now we don't have any technique which is very sensitive to these small rocky planets. But I'm excited that we have found 5,000 exoplanets so far, right? In just about 30 years, because that means on average, there's one exoplanet per star. There's more than one exoplanet per star. So any star that we look at, we should be able to see an exoplanet and learn something interesting about it, even if it's not an Earth-like planet.
So can we say that in 5-10 years, we will know more terrestrial planets in orbit around nearby stars?
That's really challenging because the main improvements that we're going to have is astrometry from Gaia, and we can use that to reprocess data from TESS and from Kepler. And there is high precision radial velocity coming online, but even that won't be sensitive enough to Earth-sized planets. We would need a next generation of instruments to be sensitive to Earth-sized planets.
Yeah, so you mentioned the radial velocity instrument. There is one being designed currently at Kick Peak, if I remember. I forgot the name of it.
Yeah, it's called NEWID, but it's spelled NEID.
Yeah, and there is Espresso at the VLT, which is supposed to reach 1 meter per second, or has reached 1 meter per second. So capable of detecting Earth-like exoplanets.
Right. So NEWID, I think, is supposed to try and reach 30 centimeters per second, if I'm remembering that correctly. To see an Earth-sized planet, we would need to reach 3 centimeters per second.
Okay. Well, so what about you yourself? What are you gonna do for the next 25 years? What's gonna be your role in those projects?
Well, it's not officially a project. Right. I do want to be clear that this has been the recommendation, and that Paul Hertz, who's the director of the NASA Astrophysics Division, has said in a town hall to the Astronomical Society that now is not the time to start a new flagship. Right now is the time to get James Webb settled. It's commissioned. We're very excited about that. It's producing beautiful results. Now is the time to work on Roman Space Telescope and get that ready. So for right now, now is the time to prepare to do IRUV, to do the next flagship. So I think there's planning would be the next thing to do. Possibly even planning the plan is the next thing to do.
What mistake shall we avoid to make this time?
I think there's still a lot of excitement in the community for this, and what the community is eager to get started on the design process, which is not just designing one telescope, but looking at a few different ideas and trading them. For example, trading, should it be deployed or not deployed? Should the primary mirror be segmented or not segmented? Should we use a coronograph or a star shade or both? And what are the costs for each of these, and what's the science return? Because it's the science that always drives missions for NASA.
So what's your personal, what would you like to do in those mission concepts at JPL? What's your role exactly? I mean, a lot of young people watch us and would like to be the next JPL associate technologies for astronomy. So what do you recommend can you tell us what you do first and what they should do in 25 years?
Right. So let me say that for the last, I spent 5 years on a concept study called HabX that was one of 4 potential future flagship studies that is like a design study that was done and given into the Decadal Survey process. And I did 2 different things. I was a technologist, which means that I have to learn about the current state of the art and what we need and what that gap is, and figure out how we close that gap, like how many years it's going to take and how many people we need working on it. And then the second thing that I did is the work that I've talked about here, which is calculating how many exoplanets we think a particular mission design can be able to see. Now, I love both of those things, so I'm still doing half my time for one and half my time for the other. So half my time as the associate technologist for JPL Astrophysics has now mean that I'm working on technology beyond just ear roof type technology. I'm learning things about other wavelength ranges, about far IR and X-ray and UV, and I'm learning about more astrophysics than just exoplanets. And then for half my time, I'm continuing to try and calculate using the models and asking new questions and trying to figure out, are there more clever ways that we can use star shades, or are there more efficient ways that we can characterize the different colors and get at these discoveries sooner? Are there ways that we can optimize how we spend mission time so that we can get more science out of the same telescope design? So I look forward to continuing to do that probably for the next 5 years. And then I would like to say to our viewers out there that are young and that are interested in this telescope design process is going to happen for a while, and then we're going to build it, and then we're going to have scientists that are going to use it. And at 20 years from now, I'll be thinking about retiring, right? And so we're going to need new generations of people to learn how to become experts, to learn how to make this technology work, to have new ideas about how to make this technology better, and about how to do the science in really compelling and efficient ways. So, I think by the time that James Webb launched, there had been over 5,000 people that had contributed to it. I expect that number will be the same or larger for your roof.
Definitely. It's gonna be a project that's gonna take the energy and the brain power of a lot of people to be able to fly and to achieve this goal, which is to image a planet like Earth. I mean,
right.
How incredible this will be, right?
This is a civilization level task, right? This requires international partnerships. This requires a lot of people. This requires the support of a lot of governments to be able to do.
Okay, well, that's a very nice way to end this conversation. Thank you very much, Rhonda, for your time, for talking to us from JPL and about this amazing idea and your work. I mean, your work is remarkable, and I'm very glad we have this 30 minutes of conversation.
Thank you. It's been a pleasure being here.
So to all our viewers, we are the SETI Institute. We are a non-profit organization. You can support us by sharing this video, commenting. We're going to take the time to answer to your questions. If you have any questions that we didn't answer to in this conversation, post them on Facebook, YouTube. You can also join us by subscribing to get our newsletter every week to learn about the science and research we do at the SETI Institute and elsewhere in the field of astrobiology. If you want to support the next generation of space telescope, we do design some telescopes as well here at the SETI Institute. You can also make a small donation by clicking on the link seti.org/give now. If you have $10 billion to build the next e-roof, let Morgan know. She will be probably interested in being in contact with you. Thank you very much to all of you for watching us from everywhere on this planet. It's always great to see this diversity of people from the world watching us to hear about the search for life in our galaxy. And thank you again, Rhonda, for joining us. Bye-bye.
Thank you.